this episode, we start moving from exam day thinking into the kind of coding thinking that makes automation behave like a dependable teammate instead of a surprise machine. Beginners often picture automation as a clever shortcut, but in operations, automation is really a promise that the same inputs will produce the same outcomes in a predictable way. That promise depends on small choices that look boring at first, like how you name variables, where those variables can be seen, and what data types you choose for the values you store and pass around. When those choices are sloppy, scripts become fragile, and fragility in automation shows up as outages, silent misconfigurations, or troubleshooting sessions that take far longer than the task ever saved. The good news is that these fundamentals are learnable, and once you learn them, many higher-level topics become easier because you can reason about code behavior instead of guessing. What we are building here is the mental discipline to write code that is ready to run in real environments where inputs are messy and time is limited. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A variable is a named place to keep a value so you can use that value later, and the name matters because code is read far more often than it is written. In automation, a good variable name tells you what the value represents and how it is intended to be used, not just what it happens to contain at the moment. A beginner might use short names like X or temp everywhere, but that creates a story where nothing is clear, and unclear code becomes risky code when you return to it weeks later or someone else has to maintain it. Clear naming also reduces mistakes, because you are less likely to mix up two values that look similar but mean different things, such as a host name versus an IP address, or a file path versus a file name. Another important point is consistency, because if you name the same concept 3 different ways across a script, you increase cognitive load and you increase the chance of introducing bugs. When you are writing automation-ready code, you are not just storing values, you are expressing intent, and variables are one of your main tools for expressing intent. Variables also allow you to avoid repetition, and avoiding repetition is not just about elegance, because it is about reducing the number of places that can go wrong. If you have a value like an environment name, a directory, or a threshold used in multiple places, hard-coding it repeatedly means you must remember to update it everywhere when something changes. In operations, change is constant, so code that resists change is code that will eventually be bypassed or abandoned. Using variables lets you centralize assumptions, which makes scripts easier to adapt and safer to reuse. It also makes it easier to validate behavior because you can print, log, or inspect a single variable to understand what the script thinks the world looks like. Beginners sometimes worry that variables make code harder, but the opposite is usually true once you choose meaningful names. A script with well-named variables reads like a set of clear statements, and clarity is a form of reliability. Now we need to talk about scope, because scope is the set of places where a variable can be accessed, and misunderstanding scope is a common reason beginners get confused by code that seems to change behavior depending on where it runs. In simple terms, some variables are visible everywhere in a program, while others are only visible inside a particular block, function, or module. The idea exists to prevent accidental interference, because if everything could see and change everything else, large scripts would become impossible to reason about. For automation, scope is also a safety tool because it limits the blast radius of mistakes by keeping temporary values local to the logic that needs them. When you keep variables tightly scoped, you reduce the chance that a later part of the script accidentally reuses a name and overwrites an important value. A beginner mistake is to treat the entire script like one shared bucket of names, which works until it suddenly does not, and then debugging becomes miserable. Understanding scope gives you a clean map of where values live and where they can safely be changed. A helpful way to think about scope is to separate long-lived configuration values from short-lived working values. Long-lived values are things like a target environment, a base directory, or a retry limit that the script uses throughout its run, and those are often defined near the top in a place that makes them easy to find. Short-lived values are things like a loop counter, a temporary parse token, or a result of a single calculation that is only meaningful for a small portion of the logic. If you treat short-lived values as global, you create the risk that they persist longer than you intended and get misused later. If you treat long-lived values as overly local, you might end up passing them around awkwardly or duplicating them, which increases complexity. The goal is balance, where scope matches the lifetime and purpose of the value. That match makes your code easier to test mentally, because you can predict when a value should exist and when it should not. Predictability is the theme, and scope is one of the ways you enforce it. Another reason scope matters is that automation often grows over time, even when you swear it will not. You start with a small task, then you add one extra check, then one more, and suddenly a quick script becomes a tool that multiple people rely on. When that happens, scope mistakes become more costly because small naming collisions and accidental overwrites appear as intermittent failures that are hard to reproduce. A variable that is meant to be temporary can accidentally become a hidden dependency for another part of the script, and then changing it breaks something unrelated. Keeping variables local to the logic that uses them helps prevent these hidden dependencies. It also makes it easier to refactor code into functions later, because local variables naturally belong inside the functions that perform the work. The exam will often test this concept indirectly by describing a script that behaves unexpectedly due to variable reuse or scope leakage. If you understand scope, those questions become less about memorizing rules and more about reading a story of how values travel through code. Now let's shift to data types, because data types are the categories of values you work with, and choosing the right type is a major factor in whether automation fails loudly or fails silently. A silent failure is especially dangerous because the automation appears to succeed while producing the wrong outcome, and wrong outcomes in operations can persist until they become incidents. Common primitive types include strings, integers, floating point numbers, and booleans, and each has behavior that matters for comparisons, arithmetic, and validation. For example, the string 10 is not the same thing as the number 10, even though they look similar to a human reading a screen. If you compare strings when you meant to compare numbers, you can get surprising results, and those surprises often show up as conditionals that take the wrong branch. When you choose types intentionally and convert types carefully, you reduce these surprises. Automation-ready code is not just about making code run. It is about making code run correctly across varied inputs. Booleans are a good example of where beginners can accidentally create confusing logic. A Boolean is meant to represent a true or false condition, like whether a file exists or whether a check passed, and that clarity is valuable. If you start representing those states with strings like yes or no, or with numbers like 1 and 0 without being consistent, your code becomes harder to read and easier to misinterpret. Booleans also interact with conditionals, and the exam loves to test whether you understand how truthy and falsy values can create accidental behavior. The safe approach is to be explicit about what a condition means, especially when the value might be missing or malformed. In automation, being explicit is not being verbose. It is being responsible, because the script must make decisions that may affect systems. When you treat decision values as booleans where possible, you also make your code easier to validate, because you can assert exactly what you expected the condition to be. That reduces ambiguity when something goes wrong. Numbers have their own traps, especially when you mix integers and floating point values. Integers represent whole numbers, while floating point values represent decimals, and floating point math can introduce rounding behavior that surprises beginners. In operations automation, this often shows up when you calculate percentages, durations, thresholds, or averages, and then compare the result to a limit. If you do not understand how the type behaves, you might create a condition that fails near the boundary, which can cause flapping behavior where automation alternates between actions in an unstable way. A stable approach is to decide what precision you need and to normalize values before comparisons, such as converting to a consistent unit or rounding in a controlled way. Another key is to validate numeric inputs, because user-provided or file-provided values often arrive as strings and might include extra whitespace or unexpected characters. If you convert without validation, you may crash, and if you skip conversion, you may compare incorrectly. The reliable path is to treat numbers as numbers and to make conversions visible and intentional. Strings are everywhere in automation because systems communicate through text. Logs are text, file names are text, and many configuration values are text. The trap with strings is that they can look like other types, and code will sometimes let you perform operations that appear to work while producing unintended results. Concatenating strings is not the same as adding numbers, and comparing strings alphabetically is not the same as comparing numeric magnitude. Strings also carry encoding and formatting issues, such as leading and trailing whitespace, newline characters, or differing capitalization, and those issues can cause comparisons to fail unexpectedly. In automation-ready code, you often normalize strings before you use them in decisions, meaning you trim, case normalize, or validate them against expected patterns. This is not about being picky. It is about preventing drift where small differences create different outcomes across environments. If a script treats prod and prod differently, that script can behave differently depending on who typed the input or how a file was generated. Reliable automation makes these transformations deliberate so behavior stays consistent. Collections, like lists and dictionaries in many languages, also matter because automation rarely handles one value at a time. Even if your script starts with a single item, real tasks usually involve sets of hosts, collections of files, or mappings of names to values. The key beginner concept is that the structure you choose should match how you need to access the data. If you need ordered items, a list-like structure may make sense, while if you need to look up a value by a key, a dictionary-like structure may be the safer and clearer approach. Misusing these structures often leads to brittle code, such as relying on position in a list when the order might change. Another important concept is mutability, meaning whether a value can change in place, because shared mutable data can create bugs where one part of the script accidentally changes data another part relies on. Even without diving into language-specific details, you should develop the instinct to ask, will this value be modified, and who else might see the modification? That instinct protects you from subtle failures in automation pipelines. Type conversion is where variables, scope, and data types all collide, because you often read input in one form and need it in another. For example, you might read a number from a configuration file and it arrives as a string. Then you need to convert it to an integer before you can compare it reliably. The safe approach is to convert early, validate immediately, and keep the validated value in a clearly named variable, so later logic does not repeatedly attempt conversions or silently handle errors. This also connects to scope, because you want the validated value to be accessible where it is needed, but you do not want temporary raw input values to leak into other logic. A beginner mistake is to reuse the same variable name for the raw string and the converted number, which can confuse you later and lead to accidental string operations on a numeric value. Using two names, one for raw and one for validated, often makes the code story clearer. When the code story is clearer, your troubleshooting story becomes clearer too, because you can identify where wrong values entered the flow. Exams reward this kind of disciplined thinking because it aligns with safe operations. Another critical concept for automation-ready code is defensive defaults, meaning you choose initial values that keep the script safe if something is missing. For example, if a threshold is missing, you might choose a default that triggers a safer behavior rather than a more aggressive one. This connects to data types because defaults should match the type and meaning of the value, not just be a placeholder. A missing boolean should not quietly become a string, and a missing number should not quietly become a zero without you deciding that is appropriate. Defaults should be explicit and documented in code through clear naming and placement, even if you do not add comments. The exam may ask about how to design code that fails safe, and a big part of failing safe is ensuring your variables start in a known, sensible state. Unknown states are where surprises grow, and surprises are the enemy of operations. When you plan defaults, you reduce the chance that a missing input becomes a dangerous action. Finally, think about how these fundamentals make automation more trustworthy to other people, because operations is rarely solo work. Code that uses clear variables, correct scope, and reliable types is easier for someone else to read, which means it is easier to review and less likely to be rejected or bypassed. It is also easier to test mentally, because you can trace values through the script without losing track of what they represent or where they change. When an incident happens, code like this helps you determine whether the automation was a cause, a symptom, or a bystander, because its behavior is more transparent. On exam day, questions in this area often boil down to predicting behavior, spotting where assumptions break, and choosing the approach that reduces ambiguity. If you understand variables, scope, and data types as tools for predictability, you will consistently choose better answers. The bigger lesson is that automation-ready code is not about fancy tricks. It is about disciplined fundamentals that keep systems stable when real life does what it always does and gets messy.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.